Okay, all right, so let's start. Last lecture we were looking at NAND gates, CMOS 2 input and 3 input, and also 4 input NAND gates. Today let's look at the other universal gate, which is the NOR gate here. And it's easy to verify that the schematic that is shown over here will carry out the NOR operation. If any of the inputs is high, A or B, it will pull the output to low, and that's the characteristics of a NOR gate here. Again, note that we are talking about fully complementary CMOS, which means that the pull down part here is complementary to the pull up part here. So we have two transistors connected in parallel, and therefore in the pull up part you have these two transistors connected in series here. So whatever happens in the pull down parts, complementary part happens in the pull up part here. So again, so functionality is straightforward, that it acts as a NOR gate. What is at issue is how do we size again? So again, we can be guided by the fact that we would like to design this particular NOR gate such that its ability to drive any capacitance is similar to that of an inverter, which means that the pull down strength under worst case condition is same as the that of a pull down strength of a inverter, and similarly the pull up strength under worst case condition matches the pull up strength of a inverter here. And under worst case condition, we know that one of the inputs may be active, so B may be 0 and A may be active here, and therefore this is rather straightforward, that we should size the NMOSs as 4 lambda by 2 lambda here. Under the worst case scenario, only one of the NMOSs is active and pulling the output node low, and therefore to match the pull down strength here and here, we should size it to 4 lambda by 2 lambda here. And we also saw the pull up part here. If the two transistors in series, when we are talking about their pull up strength, their ability, the current that they provide for charging the capacitance here, the two transistors in series, when we put both B as 0 and A as 0, their ability is effectively half of a single transistor of the same width here. So if we want 8 lambda by 2 lambda here, we should size it to 16 lambda by 2 lambda here and 16 lambda by 2 lambda here. Then effectively they will act like a single, close to a single transistor of effective width 8 lambda by 2 lambda here. So that's the idea why we are saying let's put this to 16 lambda by 2 lambda and 16 lambda by 2 lambda here. All right, so that could be, but note that the sizes are already becoming on the larger side. 16 lambda here and 16 lambda here, PMOSs are becoming large in size here. All right, the next thing is, of course, so that's the sizing here, and once you have that, you can determine the VTC. I'm not going to go through that, voltage transfer characteristics, and you can see what is the worst case condition for high noise margin and low noise margin and all that here. All right, let's for the delay calculation, we again have to go towards the layout. And so the layout, one possible layout for the NOR gate is shown over here. The two transistors are in parallel here, NMOSs are in parallel. This is connected to ground, one end is connected to ground, the other end is common. So the two transistors here, NMOSs are in parallel, and the two transistors are in series. One transistor here and the other transistor here, they are in series here, and the outputs of the transistors are connected together. Outputs are connected together, so you have V out here, and you have input A. A is for us the upper transistor here, and B for us is the lower transistor here. Lower meaning lower compared to the output here. And once we have the layout, we can have, of course, all the areas, perimeters, all the relevant areas here. These are connected to the output node here. So this is the relevant area, drain area and perimeter. This is the drain area and perimeter of the PMOS here. So these are two relevant areas and perimeters. The other one is in between. It gives rise to internal capacitance here, which is in between the two transistors here. So that area is also given here. It would be interesting to compare the two cases here. The previous one, this one over here is the NAND gate, and this one here is the NOR gate. And what is given here is, whenever I write here, so this is the area, for example, of interest, and the first part refers to the area 64 lambda square, and the second part refers to the perimeter 16 lambda. So total perimeter here is 16 lambda. Similarly, if we look at let's say this particular node here, then the total area is 56 lambda, the perimeter is 22 lambda here. And if we take note that at the output, the capacitance will result from drain to body of this and drain to body of this. So effectively we can add up the two areas here, 64 plus 56 here, so that gives rise to 120, and 16 plus 22, that gives rise to 38. So effective drain to body capacitances at this particular node come about because of an area which is 120 lambda square, and this is 38 lambda square in a NAND gate. And the internal capacitance is coming about from here, which is 24 lambda square and 6 lambda here. All right, so the important point in a NAND gate is this overall area and perimeter, and this area and perimeter here. Now compare that to the NOR gate here. So NOR gate, again, all of these are there. So at the output here, we have an effective drain to body area which is 156 compared to 120, and 46 compared to 38. So larger because of the larger sizes that you see here. And so this is not as large, I mean, the increase is not too much compared to this. But this one, the internal capacitance that you see here at this point here, internal capacitance 43 and 6 compared to internal capacitance of 24 and 6 here, 48 and 6 here. So these are almost double of this one here. So internal capacitances would be significantly higher as compared to internal capacitance here. Anyway, the overall area of the two gates are very similar. NAND gate here and NOR gate. As I said, I've not drawn it in an optimized manner. So the comparable areas. So 2-input NAND gate, 2-input NOR gate, comparable areas. But you see the output capacitance here, NAND gate is lower as compared to this. And the other part was the internal capacitance here of the NOR gate is higher here. So once you have the areas, you can calculate the capacitance. So this is what is shown over here. So this is our NAND gate, whose load was inverter. And this is a NOR gate, whose load is again in inverter. And let's compare the two. So for the NAND gate, we had calculated earlier the overall output capacitance, taking into account all the capacitances coming from the NOR gate itself and the inverter, lumping them up all here, was about 21 femtofarad. And the internal capacitance was 6 femtofarad here. Same thing if we do for the NOR gate here, we lump up all the capacitances here, 23.3, as not too much larger compared to this 21 femtofarad here. But the internal capacitance, 11.4 versus 6, the internal capacitance is significantly higher. All right, so that's what you note about the capacitances part here, when you compare the NAND gates versus NOR gate. The reason why we are doing it is both of them are universal gates and circuits you can implement with NAND as well as with NOR. The issue is which one would you prefer. Sometimes maybe you require NOR, so you have to use it, but in case you have a choice, which one would you like to use? So what we are doing is comparing the two. So these are the capacitances. Note that the NAND gate and the NOR gate have the same pull-up strength and pull-down strength, right? So we designed them with that in manner here. So anyway, so this is here. These are the delay values. This we had already obtained. We had characterized the NAND gate earlier, except that what I've done is I have written this out in terms of the delay values in terms of two components. One is the intrinsic delay, 72, for example, tau PHL intrinsic delay is 72, plus a sort of related to drive strength and multiplied by the load capacitance. The load capacitance for the NAND gate is this inverter. When I look at the inverter from here, the load capacitance is 6.2 femtofarad here. And this is that, how much does the delay increase with each femtofarad of the external capacitance here. So this is intrinsic and this is because of the load here. So total capacitance here 94 and tau P LH is 90.3, you can see, intrinsic part, and then the drive part here. 6.2 is common to both of them. 3.08 is related to the pull-up strength here. All right, if we do the same thing here, Note that tau, you can compare here 89.1. The intrinsic delay are larger. Intrinsic delays are larger here, in both the cases, 89.1 and 86 here. Note that otherwise the strengths are comparable. 3.5 tau PLH compares with tau PHL 3.55, 3.5 here, 3.1 here, and 3. Because these are complementary in nature, 3.08 and 3.1 here, and 3.5 here, and 3.55 here. So these are comparable, but the intrinsic delays are larger. Intrinsic delays are larger. The reason being intrinsic delays are larger is you can see here a larger capacitance at this node, a little bit larger than this, and this one, the internal node, 11.4 versus 6 femtofarad here. So overall then delays are also larger here, 108.6 and 107.8 here compared to this one. Right, so note that both these NAND and NOR are of comparable size, but the delays are larger. The other thing is, when I look at my NAND gate, and somebody has to drive a NAND gate, let's say somebody has to drive the input A. So these two will be shorted together. The net capacitance that particular gate sees when it drives a NAND gate versus the net capacitance that any other device sees when it drives a NOR gate here. So you compare the input capacitance here, 9.6. Why? Because you have 8 lambda by 2 lambda, another 8 lambda by 2 lambda. So if you calculate gate to source, gate to drain, all that, sum it up, you get 9.6 here. If you do that here, because PMOS is larger in size, you end up getting 12 femtofarad here. So the input capacitance of the NOR gate is higher, which means that any gate which has to drive the NOR gate has to drive this higher capacitance here, 12 femtofarad here. So that will suffer because of this larger capacitance here. The delay of the previous gate would increase as compared to the NAND gate here. So this is a sort of comparison that you see between the two gates here, NOR versus NAND, in terms of the sizes, in terms of the internal node capacitances, in terms of the delay values, and the power, of course, would depend on the capacitance. So if I switch both of them at the same frequency, note that this capacitance is a little higher than this, so there'll be more power because of this, and because of this also. This particular node will also switch under certain conditions and will consume more power as compared to the 6 femtofarad here. So in terms of power also, this is a little worse than this particular one here. Okay. Now both of these are, of course, both these gates are worse than an inverter. When I look at an inverter's input capacitance is only 6.2 femtofarad. So NAND gate is 9.6, obviously because we had to increase the size here. Size of the NMOS here compared to the size here. That's why the capacitance increased to 9.6. And this one increased because we had to increase the size of the PMOS. All right, so the next thing is, so that's as far as the 2-input NOR gate is concerned. If we build a 3-input NOR gate, now 3-input NOR gate things get even worse in the sense of transistor sizes.
Sir,
yes?
in the last slide, what do we define the input resistance? Well, like there are
input capacitance.
Input capacitance.
Uh-huh.
There are options that we can connect to, like B for B only there.
No, so for example, so B, you can connect the two B's together and the net capacitance looking at here, or you can connect the two A's together. So note that two A's will be connected together, two B's will be connected together. So you have two input capacitance, A and B, and first order they're roughly the same, and same here. Coming back to the 3-input NOR gate. So 3-input NOR gate, again, if we try to size it like our having the same strength as this particular inverter, then of course 4 lambda by 2 lambda, so all the NMOSs get 4 lambda by 2 lambda. And if this has to have the same strength as the single transistor here, note that when you connect 3 of them in series, the current is 0.15 compared to a single transistor. So the scaling factor turns out to be, for 3 of them, a factor of 3.6. So you'll have to increase, if you want to match the current for 3 series connected transistors to a single transistor, you'll have to increase the width of each one of them by 3.6 here. So what we have is an option of this, of course, 4 lambda by 2 lambda. Well, we can keep each one of them 8 lambda by 2 lambda. Nothing is stopping us from keeping size the same as this, except that note that the strength of 3 of them will become 1 by 3.6. Okay, because the current here will become 1 by 3.6 here. So strength reduces here, or you could increase it to 3.6 here. So you can increase it to whatever value you want. And the final value may be if you try to match the current here and the current here. Okay, so you multiply 3.6 by 8, maybe you get close to 30 lambda by 2 lambda. So these are the options that you have. So note that if you try to match the size, the drive strength of this, then the sizes are becoming 30. The size of the transistors are becoming even larger here. So that becomes a problem. As the size becomes larger here, note that what would happen is the internal node capacitance here and here would increase. The effective capacitance at this particular point will also increase with all the drawbacks that we saw earlier. Intrinsic delays and everything will increase. So building more complicated gates in the sense of larger number of inputs becomes a problem in this case NOR gate here. Now what I have is, it takes, to calculate the delays and everything, you have to do the layout, calculate areas and all that. So I took the data from what I've been showing you earlier from a 180 nanometer technology, one particular design. And what this particular, the data given by the manufacturer is I took the worst case values for inverter delay, NAND2, NOR2, NAND3, NOR3, NAND4 and NOR4 here. And all the delay values are given. This is pull-up delay, this is tau p LH, and this will be tau p HL. So pulling it up or pulling it down. This is related to the drive strength. How much does the delay increase if you add 1 femtofarad of external capacitor? And this is the input capacitance of that particular gate here. So you can compare, all the gates are given here. So you have NAND2, NAND3, NAND4, NOR2, NOR3, NOR4. So what we can do is, we can compare the following. We can compare, let's focus on the high to low delay. High to low delay, so this is 14, intrinsic delay of an inverter is 14 picosecond, and the drive strength is pretty good, 2.4. Note that the smaller the value, the better the drive strength, because it's picosecond per femtofarad. If my gate has a good drive ability, this factor would be low. All right, so 14 and 2.4. In the next case, look at the NOR gate here, 22 and 2.4. Now note, please keep in mind, NOR gate is what? NOR gate is of like this here. So note that 2.4 and 2.4, why is it remaining same? Because what is pulling my node down under worst case scenario is a transistor like this, a single transistor, which is also true for an inverter. And they've probably kept the same size here, so 4 lambda by 2 lambda or whatever in an inverter. The same size was kept in a NOR gate also. So note that the strength remains the same, 2.4, 2.4. But the intrinsic delay goes from 14 to 22. And then go to the 3 input NOR gate, strength remains the same, pull down strength 2.4, the delay becomes 31. And then go to 4 input, same 2.4, so we've added a 4th transistor here, it becomes 39 here. So why is this increase occurring? 14 to 22 to 31 to 39, why is this increase occurring? Because note that what is pulling it down is this particular transistor. Pull down strength is remaining constant, 2.4, 2.4, 2.4. Why is it increasing? Because of all the increase in this particular capacitance. The more the number of, as the fan-in increases from 2, 3, 4, you have more number of transistors connected to this particular node. So the capacitance at this particular node is increasing. And then you have more and more internal nodes. They also have to be discharged. And the capacitance at these points are also increasing. So that's why you see an increase in 14 to 22 to 31 to 39 here. Because of the increase in capacitance here, here, and here. All these internal nodes as well. So that's why you see all this here. You can compare, so you can see what happens as you go to more, and that's the reason why they're not going towards a NOR 5 and a NOR 6 and all that here. Note that this is only 39, but look at the other side here, pull-up. The pull-up has gone to 121. So if I start comparing the pull-up part here, 23, 45, 82, and 121. So look at the pull-up delay, how much it is increasing. So for that reason, again, as I said, you won't increase. And then compare also the pull-up strength, 4.5, 6.7, 8.5, and 9.4. 9.4, what does it mean? For every femtofarad of capacitor, delay will increase by 9.4 picosecond here. So you can see why one would not go and make a larger fan-in NOR gate here. NOR 4 is the maximum, at least this particular manufacturer provides the NOR 4 as the maximum fan-in gate here. The other thing is, let's compare the NAND and NOR. NAND and NOR, NAND 4 and NOR 4. If you compare the NAND and NOR, and I've given the areas that the manufacturer lists. For the NAND, the area is 5 microns into 3.3 microns here, and for the NOR is 5 micron into 4 micron here. So the NOR gate, note that 4-input NOR gate is a little bit costlier as compared to this in terms of area, higher area here. And you compare the worst case delays. So worst case delay in this is 66, and worst case delay here is 121, almost double NOR 4. So larger area and almost a double delay here, 121. And not only that, look at the strength. NAND 4 gives you 4.4, and this gives you 9.4 here. So anything that you add to your 4-input NOR gate will get multiplied by 9.4 as compared to 4.4 here. So clearly in this case, you can see and both of them have this one also has a greater input capacitance, 4.8 as compared to 4.5. So on all counts, if you look at a NOR versus a NAND, on all counts, this takes up a little higher area, it has a higher input capacitance, and it has higher delay, intrinsic delay, and it has a worse strength. On all counts, you find NOR 4 is inferior to NAND 4 here, in terms of all the delays as well as area that you see here. And you can clearly see that NOR is for that reason, is not as preferred as compared to a NAND gate. NAND gate is preferable in this fully complementary CMOS for implementing your design as compared to NOR because of the reasons that you see over here. Okay. All right. This particular issue we had raised earlier, we've been saying that, well, when we take a transistor, size all of them the same, maybe 8 lambda by 2 lambda, size all of them the same here. But that's for simplicity. If you wish, you can change the sizes of size of this one and size of this one could be different. And one of the thinking is, let's say what would be the benefit that would come from unequal sizing? Well, let's suppose we are looking at the pull down delay. This is the output node, and if I want to pull it down, under worst case scenario, I'll have to discharge this particular capacitor. It is initially charged. I'll have to discharge this, I'll have to discharge this, and I'll have to discharge this. I'll have to discharge all these 4 capacitors here. And as a very simple case, one could look upon this discharge where we model the transistors as resistors, let's say. Just qualitatively, each transistor, let's say if I model it as a resistor here. So this discharge is like this here, this one here, this one here, and this one here. All right, so a very simple RC model of the discharge path could be built in this particular manner here. Now, if we look at this one, capacitor C5, when it discharges, of course, the net resistance. So if I want to calculate the time constant by considering one capacitor at a time, so C5 sees R5 plus R6 plus R7 and R8. It sees the whole resistor here. C6 sees R6, R7 and R8. And C7 sees R7 and R8. And C8 only sees R8. So in terms of importance, which resistor is the most important? R8, all of them see. R7, then, the 3 of them see. And then R6, 2 of them. And R5, only this one sees. So in terms of importance, the most important resistor, if I look at this, appears to be this one. So maybe if you want to make it one, if you had one transistor to increase the size, maybe, or if you in order of importance, maybe you would try to do it in this particular manner here. M8, M7, M6, M5. If you had to make it unequal, maybe make the size of M8 the largest, whatever largest size you can accommodate, then you make the size M7, then you make M6, and then you make M5 here. All right, so maybe this sort of makes sense in terms of the unequal sizing here. Well, as an example, I was looking at it. This illustrates how much change can you get here. So, for example, look at this. I have 4 transistors in series here. All of them are 8 lambda by 2 lambdas and all that here. is actually a NOR gate. I have not shown the other transistors here. So let's focus on the high to low delay when all of them are of the same size. And for simplicity, this one was 21 femtofarad, all the internals were kept at 6666. This may not be very realistic, the sizes and all that may change, but anyway, tau PHL is 238 picosecond. All the sizes are the same. In the next case, what was done was only the size of the top one was increased to 16 lambda. Others are still 888. The delay decreased to 210, 238 to 210. Note that as you increase the size from 8 to 16, the size of the capacitor here would also increase, but I didn't do that. I kept all the capacitors still the same. Okay, so just to highlight this, so it becomes 16 lambda by 2 lambda, 210. On the other hand, if you leave its size 8 lambda, all of them 8 lambda, and double the size here, the delay becomes 201. 201. So this transistor has more impact on delay as compared to M2 here. And that we saw because M2 affects only the discharge of this capacitor, while M8 affects the discharge of all of them. Okay, so this one is more important as compared to this particular one here. All right. So we've seen NAND gate and NOR gates very quickly. Remember, we were looking at this as a part of a homework problem. What function does this particular gate perform? So we saw that this is AB, this is CD, and then these two are in parallel. So it's an OR operation, and then of course everything is complemented because this whole thing brings the output down here. So complemented here. If I want to size again in terms of if I have to match the drive strength here, then note that these two are in series. So I will have to sort of double the size here. So each one of them becomes 8 lambda by 2 lambda here to match the strength here. And again, pull up, if I look at the worst case pull up path here, so either it is one transistor and another here, or whatever, one here and another here, whichever way. So again, I have two paths, two transistors in my path here. So if I want to match the strength here, each transistor becomes 16 lambda by 2 lambda here. So as a rough design rule, if you're matching the strength here, then this is what you will end up doing in terms of the sizes here. But as I said, if this is increasing your capacitances and all that too much, you may want to reduce it further also. So you can, for example, choose this as 12 lambda and this also 12 lambda. You could do that, except that then the drive strength of the pull-up part would be inferior to that, and the delay values and all that would increase here. But given the problem, if it says match the strength here, then this is what you end up doing here. 16 lambda by 2 lambda, 16 lambda by 2 lambda. All right. This we had seen earlier, how to construct a NOR gate here. So let's skip that here. Now, is this the only way in which we can implement logic, for example, NAND gate and NOR gate? It turns out that we had seen earlier resistive, a NMOS logic with resistive load. So there are several other logic families available. You can call them logic families, or you can call them different styles of implementing a circuit. And when you're looking at different logic families, these are the dimensions along which you compare them. What we're looking for is simplicity. Simplicity in terms of the area that my NAND gate or an inverter or a NOR gate occupies. We're looking at fast logic families as fast, so delays tau PHL and tau PLH should be low. We're looking at low power operation. We're looking at good VTCs, high noise immunity. And we're looking also that my logic family scales well with fan-in. As the number of inputs of NOR gate increases or the number of input of NAND gate increases, it scales well. Scales well in the sense that the delays do not increase too much, and neither does the area increase too much as you increase the fan-in here. So these are the dimensions along which you can compare the different logic families. The area part, the delay part, the power part, the noise immunity, and how it scales with fan-in. All right, so with that in mind, if I look at fully complementary CMOS, fully complementary CMOS that we've been seeing is here. 4-input NAND gate, 4-input NOR gate here. If we look at these fully complementary CMOS, well, the one that I've highlighted in red are the strengths of this particular logic here. Low power, there's no static power dissipation. That's a good part of this particular design here. Although dynamic power, if I look at any particular node here, this one, it gets a contribution from all of these transistors here, it gets a contribution here. The dynamic power may not be as low for this one. But static power is certainly absent, so that's a good part. Noise immunities are in general better here for this particular one. And it's not necessarily simple. Note that if you have 4 transistors here, I have 4 here. I have 4 here and 4 here, and we have seen that the sizes of these 4s, they become larger in order to match the drive strength. So either the size here is increasing or the size here is increasing here. So it's not necessarily simple in terms of area. It does occupy a significant area. It's not that fast. Why? Because the capacitances are increasing at this particular node. And as you can see here, it doesn't scale that well with fan-in. If I want to build a 5-input or a 6-input NOR gate or a NAND gate, it becomes difficult. So it doesn't scale well with fan-in. And all these are problems with this particular logic here. The strength is here. Now, the other thing about, you will hear the phrase that this is a ratio-less logic. Because when we look at other logic families, you'll hear the word ratioed logic and ratio-less logic here. So what do we mean by that? So anyway, capacitances and all that. Ratio-less actually logic, when we say that, it basically means, note that when we construct a NAND gate like this, a NOR gate like this here, the freedom that we have is the sizes, right? Or size here and size here. Now, when we say something is ratio-less, that independent of what size I put here and what size I put here, the logic high level is 3, the logic low level is 0. The logic high and the logic low, they do not depend on what are the sizes here, the ratios of the sizes here. That's why we call it ratio-less logic. In other logic families, this may not be true. Depending on what size, I'm sizing these to affect my delay and all that, what sizes I put here and what sizes it may put here, it may affect my logic low value here. It will not be 0, or it may affect the logic high value here. All right, so those we will call it as ratioed logic, where the output is high and low values depend on the ratios of the sizes of the PMOS and the NMOS here. So this is a ratio-less logic that's also cited as an advantage. I can put anything here and I can put anything here, still I get VDD, still I get 0. It works fine. All right, the other one that we saw earlier, so this is our CMOS, fully complementary CMOS. This logic we had seen earlier with NMOS transistors and with the resistive load. And if we evaluate this along the dimensions that we just said, is it simple? The answer is no. It's not simple because the resistor occupies a large area. Is it fast? The answer is again no, because the resistor has to pull up this particular node. It's very poor in pulling it up. So that's also bad. Is it low power? The answer is again no, because it has static power dissipation. When I apply a high input, then when output is low, we have static power dissipation. And it doesn't have a good noise immunity, doesn't have a good VTC also, doesn't have high gain and all that. So none of these things are positive. All these are negative for this particular logic. This is good here. It scales well with fan-in for NOR gates. If NOR gate is a universal gate, and I can build, note that inverter would have had only A here. And 2-input NOR gate, you add another transistor. 3-input NOR gate, you just add one more transistor. And under worst case condition, only one of these transistors is active. So if this were 4 lambda by 2 lambda, you can keep this 4 lambda by 2 lambda, you can keep the third one also 4 lambda by 2 lambda. So it scales well with fan-in. Except that this is a ratioed logic also. Because the output value, note that when A is 0 and B is 0, when all of these are 0, then the output is stable VDD. Doesn't matter what RL is there and what sizes are there, fine. But when A is high, then the output value here is supposed to be 0. But then it depends on what value of RL I choose here and what size I choose here. So it's a ratioed logic. It's a ratioed logic, so the output value depends on the sizes here. So for example, for an inverter, I will have a certain value of V0L. When I add one more transistor here, I'll have another value of V0L. When I add one more, I'll have another value of V0L. So the value depends on how many transistors are there, what the sizes are. So it's a ratioed logic, but this is an advantage. This is a very positive part of this particular logic here, that you can build large input NOR gates. I can put 4 input NOR gate, 5 input NOR gate, 6 input NOR gate, scales very well. Very well with this. All that you need to do is add one more transistor. Okay, so this is a very positive feature. And then if we start with this positive feature and we say, how can we keep this positive feature of this particular logic and try to eliminate the negative points here? So the first negative point, so we want to preserve this. So we want to preserve this part here, that is, we can build very high input NOR gates, large fan-in NOR gates here. But we want to eliminate these disadvantages here. So the first disadvantage that you see is that, well, it's not very simple. The reason being is that the resistor here occupies a large area. So the idea is, well, replace the resistor by a transistor. Transistor doesn't occupy much area here. So that leads us to the next logic, which we call as the NMOS logic, where we try to replace the resistor that you see here with another NMOS transistor. Another NMOS transistor, but with this gate and source shorted together. It's a specially constructed transistor, which we call as depletion mode. Its threshold voltage is negative. So normally, even though you put VGS as 0, the transistor is on, and so it behaves similar to our previous logic, except that we have eliminated 2 disadvantages. This is also now simple, because it's no longer a resistor. This also occupies less area. It becomes faster because this is better than our previous resistive load here. So it's better in terms of speed, faster here. But power is again a problem, because when the output is low, there's a direct path from VDD to ground. So static power dissipation is still an issue. Noise immunity doesn't have a very good VTC. Noise immunity is still a problem. It's a ratioed logic. The output value here, the output load depends on the size here and the size here. It's a ratioed logic here. All right, so at least 2 of the disadvantages have been eliminated by going towards this kind. But note that a separate disadvantage comes because in my fabrication process, I need to construct another kind of a transistor, which is a depletion mode. A depletion mode with a negative threshold voltage. So that's another process complexity that comes in here. Now, some of these things that you see here can be preserved if I go and don't use an NMOS with this thing, a gate and source shorted together. If I go towards this one here, and you can see why this logic has a name Pseudo NMOS, because historically this came first. Historically, this logic came first with an NMOS here and an NMOS here, so it's a purely NMOS logic. And this one acts as a load. The load is always on, gate to source shorted together, negative threshold voltage load is always on, and this is the one transistor with switches. Now when you take this NMOS and you replace it by a PMOS which is connected here, so the load is always on. This one gate source to gate voltage is larger than threshold, this is always on, and it has the same structure as the previous one, except that we have taken the NMOS and replaced it by PMOS. So that's why the name goes as Pseudo NMOS. It's like the NMOS logic that we saw earlier, except that it's not purely NMOS. We have taken the NMOS part out here and replaced it with PMOS. So it preserves the same advantages. It's simple, it's fast, scales well with fan-in, you can build large input NOR gates, but still has a problem, low power and noise immunity. All right, so this is what we call as the pseudo NMOS logic here. So this is frequently used whenever you want a large fan-in gate. For whatever reason, if you want a 20 input NOR gate. All right, so where would you require a 20 input NOR gate here? Well, if you look at this, NOR gates are used for implementing sum of product expressions. So if you have a Boolean expression like this, x0, x1, x2, x7 plus whatever, right? Suppose you want to implement this whole thing as a one single gate. One single gate. Well, we have seen that you can take this expression, cast it in multi-level form and all that, but that requires effort. That requires effort to break this into a multi-level form. So very quickly, if you have an expression, you minimize it, you may get something like this. And then you can implement it using a large AND gate and a large OR gate that you see here. Right? So you require, depending on the number of terms here, you may require very large AND gate and very large OR gate here. So the idea is that you can see obviously that with an AND gate you can implement using NOR gate, and OR gate of course you can implement using NOR gate again. So if I can build very large NOR gates, very large number of, large NOR gate meaning with large number of inputs, then it becomes easier to implement this Boolean expression in a straightforward form. And this is what this particular logic allows. Very large number of, you can build a 10 input NOR gate. All that you need to do is put 10 such transistors here. Each one of them of the same size, 4 lambda by 2 lambda, 4 lambda by 2 lambda, so you put 10 of them. And of course we'll have to size this appropriately so that you get proper V0L and all that. And you get a reasonable 10 input NOR gate. Doesn't occupy too much area, it remains simple. As compared to other alternatives, it is fast. Note that every time you add a transistor, every time you increase the fan in from 2 to 3, all that you're adding is one more transistor here. So the capacitive loading doesn't increase much. The loading of this particular node doesn't increase much as compared to a fully complementary CMOS. Every time you go from fan in of 2 to 3, you add a transistor here, but you add so many more transistors at the other part also. Okay, so the loading of this particular output is not very high. So that keeps the capacitance. The input capacitance is also not very high. Input capacitance of for each input remains the same. Okay, so these are all benefits. So if you can live with this power part here, then this is an excellent gate. You can build a 10 input NOR gate, and with that 10 input NOR gate, you can build an OR and an AND and all that. So it's a very nice feature of this particular one, but power is an issue. So people have thought about, can we again sort of preserve the advantages of this one, all the advantages that you see here, and get rid of this power? Okay, so one has started from there, and can we get rid of power here? So one of the alternatives that we see here is a logic shown over here, which is called differential cascade voltage switch logic. Complicated name, but look at the idea behind it. Look at the idea behind it. Remember earlier what it was? Keep this in mind here. Keep this logic in mind. Which one? Our pseudo NMOS. One PMOS and all these NMOSs here, right? All these NMOSs here. So what this particular logic is saying is the following. Look at this one here. So every logic, remember, will have a pull down and a pull up. So in these cases, the pull up is a 1 PMOS here. 1 PMOS here. So normally in the pseudo NMOS, I had a pull up and I had a pull down network. Now what we are saying is there's a pull up here, M2, and a pull down network here. There's another pull up here and a pull down network here. And the two pull down networks are complementary in nature. Complementary in the sense I designed it such that if this pull down network is active, that it creates a path to the ground, then this one is inactive. If this one is active, then this one is inactive. That's how we design PDN1 and PDN2. Okay, so that's how the two are designed. And note that what happens is, if PDN1 is active, note that if this path is active, then V01 is 0. This is 0 here. And the 0 here will go here, will turn the PMOS on, and this part is inactive. If this is inactive, there's no path to ground, so this output is high, and this high will go here and will turn it off. So note that I don't have a direct path from VDD to ground. I don't have a direct path from VDD to ground, so there's no static participation. Either the pull down part is on, and then M2 is off, or M1 is on, and this is off. So the whole idea behind this particular logic was to build something like the pseudo NMOS, but eliminate the power. And so they're eliminating the power by adding this. But then in the process, what did they lose? The simplicity. Whatever was here, part here, they replicated another part here, two pull down networks. So I would put this as a question mark here. It doesn't retain the simplicity of that other one. Okay, that much here. It's also ratio-less. Remember, logic will become ratio-less if only the pull-up part is active or the pull-down part is active. It's only when both of them are on that, the size of this and size of this affects the output value here. But if only one of them is on, if only M2 is on, then of course the output node is VDD. If only PDN1 is on, then the output value is 0. It doesn't matter what the ratios are. is when both of them become active at the same time, then my logic becomes ratioed logic here. So it's a ratioless logic and all. Let me show you an implementation here. Number of gates, if you look at here, number of gates in this, transistors in this particular gate is, would appear to be 2m plus 2. If m is the number of gates here, then m is the number of gates here, complementary, m plus m, 2m, and then 2 here. So it would appear to be 2m plus 2, but it's not exactly like that. So let me show you an implementation for an XOR gate. So XOR gate PDN1, first one. I'm building an XOR gate. So PDN1 is AB bar plus A bar B. So whatever is the gate that you're building, whatever is the logic function, take its complement, and that forms the pull down network. So AB plus A bar B bar. The pull down network is complement of PDN1. So you take the complement of this becomes here. All right. Look at the PDN1 and PDN2. Maybe what I should do is PDN1, so that you can see here, copy here, and put it here so you can see clearly. All right. Okay, PDN1. You can see AB, A bar B. This is a normal PDN1, and here. All right. Okay. So we can see better here. All right. So and this is the complementary part of this. So the idea is that it's not always 2m plus 2. So what they do is they share the transistors here. Note that there is an A here, and there's an A that you want here also. A is going to a transistor and is connected to ground. A is here and connected to ground. So this part and this part are shared together. So you connect A here to the ground, and this B is on top, and then B bar is here, so you put B bar here. So sort of sharing of transistors, and similarly you see both of them, and you try to share as much as possible between the PDN1 and PDN2. So the idea is that the logic is not as complicated as it seems, that the number of transistors will be 2m plus 2, but sharing will make this particular logic more efficient. Anyway, so it's an interesting concept. I don't think it's used too much because perhaps it's not as simple as it lost some of the advantages of the pseudo NMOS that was there by building a complementary part here. All right, so this is our the differential cascade voltage switch logic here. So that's the key idea here. The other one, which is also very popular, is called pass transistor logic. The idea is very simple here. The idea is very simple. You can see that I can construct a logic, let's say an OR gate. If I had two switches available to me, I can construct an OR gate in this particular manner here. You can easily verify if A is 1. If A is 1, the switch closes. A is 1 here, so the output is high. On the other hand, if A is low, 0, the switch is open. A bar is 1, the switch closes, and whatever is B goes here. And if B is 1, the output is 1, and if B is 0, output is 0 here. So it acts as an OR gate. Very simple implementation of a OR gate. Very simple implementation of an AND gate. Note, if A is 1, the switch closes, and the output becomes equal to B. If B is 1, then of course NAND gate output is 1. If B is 0, then the output is 0. Why is this needed? Is this redundant? Can I build a AND gate by simply taking B, put a switch, and then connect it to the output? If A is 0, then what happens? The switch is open, and what happens to this particular node? Well, this particular node is floating. If I didn't have this, this particular node becomes floating. And so if this node were earlier high, it would remain high, but I have to pull it down. So that's why this part is needed here. So when A is 0, this closes here, and this becomes 0 here, and it pulls this particular node down here. So note that both AND gate and OR gate and AND gate are so simple to implement. All you need is two switches. Similarly, in fact, look at this XOR gate, this XOR gate. Compare that with the fully complementary CMOS. Fully complementary CMOS, look at the number of transistors, upper part, the lower part, and look at this one. And if we assume that the inverter, the A and A bars are available, like we are assuming here, A and A bar is available, so I don't really require an inverter. Suppose A bar is available. Again, 2-switch implementation of a XOR gate. Versus you can verify A B, and you can verify as compared to this one. Looks very attractive. Two switch implementation of a XOR gate. Similarly, 4:1 mux. Look at this implementation of 4:1 mux. So the idea is then again, all I need is 8 switches. And the idea is that, well, the switch I can perhaps just use an NMOS transistor or a PMOS transistor as a switch. Well, we'll see what happens. But so the idea is that if each switch can be a transistor, so note that the whole thing can be done in 2 transistors. XOR gate in 2 transistors compared to this. And similarly, the entire 4:1 mux and 8 transistors looks very attractive. Looks very attractive. That past transistor logic is the thing to do, right? So we will see what the disadvantages of this one are and how to overcome some of those. But again, it's an attractive way of implementing logic with this kind of a concept rather than the fully complementary CMOS that you see here. Okay. All right. So let's stop here.